Moving on to identifying redox reactions. And reduction always have to occur together. So if something loses an electron, that electron can't just disappear or just leave in a regular situation. It has to go to another element. So oxidation is an increase in oxidation state, loss of electrons. Remember oil rig. So oxidation is loss, reduction is gain. So in this reaction, we've got two elements in their elemental forms, or at least one of their elemental forms, really written by themselves without a charge. So their oxidation states are 0. But then when we form this compound now, we have to assign oxidation states. And then we can see that carbon goes from a 0 to a +4, and sulfur goes from a 0 to a -2. So we've got a transfer of electrons. Carbon loses 4 electrons. Sulfur, I guess the two sulfurs gain 4 electrons. So carbon goes from 0 to +4, loses electrons. So it loses electrons and is oxidized. Sulfur gains electrons and is reduced. So in any chemical reaction then, we got to look for these signs that oxidation states are changing. One of the easiest places to look is if you have any elements, if they form a compound, that's going to be a redox reaction, especially if it's a metal. First, we just want to use oxidation states to identify the element that is oxidized, the element that is reduced. We need to know where everything is at and what its oxidation state is. So what's the oxidation state on tin? 0. Oh, first tin. So let's write these underneath. So tin's oxidation state of 0. And what about nitric acid? Which oxidation states get assigned first? Hydrogen, it's +1. Then oxygen would be -2. Nitrogen, so this is +1, say +x, plus -6, because there's 3 of those. That has to equal 0. So really it's x plus -5 equals 0. So nitrogen has to be +5. Now in tin oxide, what's the charge? Or I guess which oxidation state do we assign first? Oxygen. So oxygen's -2. What is tin? +4. Because there's 2 oxygens, so -4, so this has to be +4. How about nitrogen dioxide? Again, what gets assigned first? Oxygen again. So nitrogen is +4. And water is nice and easy because hydrogen and oxygen both get their preferred oxidation states. Okay, now we look at the whole thing and we say, what changed oxidation state? And we go element by element, right? So did tin change oxidation state from reactants to products? Yeah. So it goes from 0 to +4. So did it gain or lose electrons? Loses. Because you lose an electron, become more positive. So from here to here, that's -4 electrons. So, yeah. The losing electrons, making things more positive is, yeah, a little hard to wrap your head around. But you're losing negative charges. Yeah, so it's losing electrons, so it's being oxidized. Oxidation is lost. Now, technically, it's the tin metal that's being oxidized. Because being oxidized, the oxidation, it's a process. What else is changing oxidation state? Yeah, the nitrogen is the one that changes. Goes from a +5 to a +4. But if we just check, hydrogen's +1, still +1. Oxygen there is -2. And then everywhere that it is, in the products is still -2, so the oxidation state of oxygen doesn't change. So nitrogen is the other one. And does it gain or lose electrons? Gains, right? So really each nitrogen's getting 1 electron. In total, there are 4 for this reaction, though. So gained, reduction is gain. And again, it's the nitrogen in the nitric acid that's being reduced. Nitrogen. So the tin is being oxidized, and the nitric acid, or the nitrogen, more specifically in the nitric acid, is being reduced. And this is why on Wednesday or Friday, depending on which lab you're in, we'll talk about the whole scheme for balancing these. Because when we have these transfers of electrons, it's not super obvious why it's balanced this way necessarily. But in the end, there's a 4 on the nitrogen dioxide because, and a 4 on the nitric acid because we need 4 electrons to be transferred from the tin. But it's a whole process. Okay, any questions? Nope. All right. I think he's got back. Oh yeah, so oxidation and reduction must occur simultaneously. So that's why it's part of this chemical reaction. The nitrogen's picking up all these extra electrons from the tin, changing the charges, changing the oxidation states. And this is one of the more confusing things in this class. The reactant that reduces an element in another reactant is called the reducing agent. The reducing agent contains the element that is oxidized. And then it's the opposite for the oxidizing agent. It's really confusing because the thing that's being oxidized, I gotta make sure I'm gonna say this right. The reducing agent contains the element that is oxidized. So the thing that's being oxidized is the reducing agent. And it's that flip-flop that's super confusing. So just know that oxidizing agent, reducing agent are the opposite of what is being oxidized and what is being reduced. So always find oxidized and reduced first. Then you flip it and it's the other agent. Find what's being reduced, it's the oxidizing agent. Find what's being oxidized, it's the reducing agent. Don't try to find those first because it's way more confusing. We've got a nice mnemonic for oxidation and reduction. Oxidizing agent, reducing agent can be found as the opposite of those. It's called the oxidizing agent or the reducing agent because it's sort of causing the other thing to be oxidized or reduced. So we go back up to this problem. That's what we did. Our first step was finding what's oxidized, finding what's reduced. So what's my reducing agent? The one that's oxidized. So tin is oxidized. It's the reducing agent. Nitric acid here being reduced, so it's the oxidizing agent. So just remember how to find what's being oxidized and what's being reduced, because reducing agent and oxidizing agent, you just flip it. Much easier to find the first one, oxidized and reduced. Okay. When you're doing redox reactions. So talk about on Wednesday or Friday, again, depending on which lab. Okay. And of course, we're going to do it right now. All right, so lithium and chlorine reacting to get lithium chloride. So first we want to assign oxidation states for what we have. So lithium here is 0. Chlorine is 0. Lithium and lithium chloride ionic compound, so we can use the charges. Okay, so what's being oxidized? Lithium. Oxidation is loss. So what's being reduced? Lithium is the reducing agent. And chlorine is the oxidizing agent. Oxidation is loss. Reduction is gain. Ah. All right. Okay, just not enough space. Let me do it like this. Lithium. Okay. So oxidation state of aluminum. Yep, doesn't have a charge by itself. 0. And tin, 2 plus. Plus 2. Technically, it switches when you do oxidation states. Aluminum 3 plus. Plus 3. And tin. Okay, so what's being oxidized? Aluminum's oxidized. And what's being reduced? Tin. Yep, so tin is also the oxidizing agent, and aluminum is the reducing agent. In a different context where you're like talking about reagents that you want to use for a reaction, maybe it would be useful to say, oh yeah, I've got chlorine is going to be my oxidizing agent. It's going to reduce something else. It's going to oxidize something else, so it itself is being reduced. I'm trying to think if there's a faster way to do this. Oh wait, it's the first part. Okay. Does it look like anything in this? Real quick check, first check you can do with redox reactions to see if it is a redox reaction is for ionic compounds, just look at their charges. Or think about their charges as their oxidation states. So lead here would have a charge of 2 plus, so its oxidation state is going to be plus 2. Yeah. Lithium here would be, yep. Chloride, I should say. And then in the products, notice I skipped nitrate because really it would be nitrogen, but I'll show you what to look at that in a second. Does the charge of lead change? Nope, it is still plus 2. And chloride? Minus 1 for each chlorine, yeah. And then, oh, lithium is still plus 1. So that's 3 of the 4 things in the reaction. Their oxidation states didn't change. So that means that nitrogen and oxygen can't have changed. The other thing we could look at here is this is still nitrate. Right? This is still nitrate. This is still nitrate. So nothing changed in terms of oxidation states. This is just a double displacement reaction. So is it redox? No. Yeah, you can assume that the nitrate has a minus 1 charge. Because it's part of ionic compounds in this case. All right, so number 4, is number 4 a redox reaction? What are the initial oxidation states? 0 and 0. But in a compound, we would assign oxygen first. So this is negative 2. Carbon would be plus 4. And really, for the purposes of this, I guess you could just say plus or minus. If we're just trying to do oxidized or reduced. So what's being oxidized? Carbon. And what's being reduced? Oxygen. And that's the reducing agent and the oxidizing agent. Cool. Any questions about that? Assigning oxidation states. Then remembering that you lose electrons and so it becomes more positive. Okay. Activity series. So this is predicting whether a redox reaction is spontaneous. And this is mostly when you have 2 different types of metals. Actually saw a TikTok not too long ago of somebody who had a steel bowl and they had made ribs in it or something, or they had stored ribs in it. They cooked something and they were storing it in there, and they had an aluminum foil over the top. But all of the spots where the ribs were like poking up and touching the foil, it had eaten holes through the foil. And that's because through the meat and the bones, the steel and the aluminum had undergone a redox reaction and had actually turned the aluminum into aluminum oxide. And somewhere some steel, I guess, was... No ribs were harmed. Well, yeah, except for the cow or... Yeah. Anyways, so you can predict these reactions depending on this activity series. And the key thing I want you to focus on here is the magnesium has a greater tendency to lose... Really, it's actually... Hold on. Tendency to lose electrons. So activity series is all about a tendency for different metals to lose electrons. Some metals lose electrons more easily than others. When those two metals come into contact, the metal that loses its electrons more easily will just give them up, or the other metal will take them from it. So in this example, magnesium and copper, the blue color from the copper 2+ fades, and then solid copper appears. It's not pretty copper, but it's there as the magnesium is being oxidized. The activity series is just basically that. If you take a copper strip though, copper metal, magnesium 2+ solution, because the magnesium loses the electrons more easily than the copper does, magnesium here has already lost all those electrons, and thus copper has no electrons to steal from the magnesium. So these are reactions that are spontaneous only in one direction. So you could, in theory, have a whole series of metals that you stick into different solutions, constantly swapping the electrons from the most easily lost to the less easily lost. And when we're doing oxidation reduction reactions or redox reactions and balancing them, we're also going to look at these as reaction half, or as half reactions, just like they're going to be in the activity series. And this list that's going to follow is the oxidation side of all of these half reactions. If you take one of those reactions and flip it around, then you get the redox. Not the redox, the reduction half reactions. So you got to have two things to make one full reaction. This is where I made that meme. It's getting a little old. It's bad luck, Brian. Most likely to lose an electron. He's right up at the top of the list. So basically, lithium is the most likely to lose an electron. So you pair lithium with anything else, and lithium metal will lose its electrons to anything else. No, you don't have to memorize this. You need to know how to use it. So if I say this metal and this metal, or this metal in a solution of this ion, does a reaction happen? And you're just looking at which direction you're losing electrons. So these are the, again, oxidation potentials or oxidation half reactions. Not potentials, that's Chem 2. Right? Because I have lithium, it's got the electron in the reactant side. In the products, now it's lithium and an electron, so it loses that electron. If I was to write any of these the other direction, like Li plus goes to, or sorry, Li plus E minus going to lithium solid, reduction is gain, the lithium gains the electron, so that's the reduction reaction. So if we look on this list for magnesium and copper, so magnesium's higher on the list, it's more likely to lose electrons than copper is. So if I put magnesium, if I take magnesium metal that has electrons and I pair it with copper that doesn't have electrons, the magnesium is going to give those electrons up to the copper, and so this would have a reaction. So the metal on this list will react with any ion lower than it on the list. There's two questions here, right? Yeah. Okay. So which metal is most easily oxidized? Sodium, chromium, and gold. Sodium, chromium, gold. Which one's the most easily oxidized? Sodium. Oxidized, more likely to lose electrons. So it'd be sodium would be the most, chromium would be second, and gold would be third. Okay. Let me do this. Okay. So is reaction A, is it spontaneous? I should ask this question first. Which one's more likely to lose electrons? Zinc. The zinc here. And then we've got the nickel below it. Now, over here, I don't have nickel, I've got Ni2+. So I have this ion, so that wants to gain electrons, because I have the Ni2+. So zinc is more likely to lose electrons than, zinc is more likely to lose electrons than nickel is. So it is spontaneous. And for this next one, zinc and calcium. So calcium's more likely, calcium metal would be more likely to lose electrons without Ca2+. Here I've got zinc metal, less likely to lose electrons, would not be spontaneous. That's activity series. I think there were Alex questions for that. That's one that's just practice helps a lot. So look at your metal first. So we got zinc. So zinc, for the first one, the ion nickel is below it. So for both of these, we had the zinc metal. So look at there, I've got zinc metal. Now for the first one, it's zinc and then the nickel 2+. So I'm comparing zinc and then nickel down here below it. Do you think that? Yeah. Where the top was the least likely to lose an electron? if you want to rewrite the table.
Is it because you're reading them in order?
I'm comparing the metal version of this one. So if I rewrite this as so now I've got calcium solid. We got calcium with no charge. Is going to lose its electrons to the zinc 2+. So I guess one way you could put it is if the ion is lower than the non-ion, the ion's lower than the element.
Will the chart be provided for us?
Yeah. Yeah, I'll provide a chart. Yeah, you could read it in the other direction as like lithium. This is the most likely to lose an electron. Don't read this plus as addition. It's just saying there's two things. It's losing an electron. So it goes from lithium, and the electron is there, part of the lithium. After the reaction, should gesture that way maybe. After the reaction, you have lithium and an electron. Calcium is very likely to lose 2 electrons. Yeah. I could just pick more ions and we could compare them. Yes, no. Gas law chapter is also very long. Did I just send a message?
Yeah.
Huh? All right. Yes.